Good afternoon, everyone. Today I'm excited to give a presentation on SARLock, which stands for SAT Attack Resistant Logic Locking. This is a critical area of research in the field of hardware security, particularly in the context of securing integrated circuits against various threats. My name is Sushant, and I'll be guiding you through this presentation. We'll start by understanding the security challenges in the globalized IC fabrication chain, and then delve into the concept of logic locking and explore the SAT attack, and finally discuss how SARLock provides a robust solution to these challenges. Let's get started. Before we dive into the details, let me give you an overview of what we will be covering today. The presentation is divided into five main sections. First, we will discuss the introduction to security threats in the IC fabrication process. Next, we will explore the concept of logic locking, which is a technique used to secure IC designs. Then we will look at the SAT attack, a powerful method used to break logic locking. After that, we will introduce SARLock, a novel approach to resist SAT attacks. Finally, we'll conclude with a summary of our findings and the significance of SARLock in hardware security. Let's start by understanding the security threats in the globalized IC fabrication chain. IC fabrication is an expensive and highly complex process. Most companies today operate in a fabless model, meaning they design the chips but outsource the manufacturing to the offshore foundries. While this model reduces the cost, it introduces significant security risk. The foundries may not always be trusted, and they could engage in IP piracy, where they steal the design and sell it illegally. They could also produce counterfeit chips, which are cheaper but unreliable, or they can even insert hardware trojans, which are malicious modifications that can compromise the chip's functionality. These threats not only lead to economic losses but also result in unreliable products that can fail in critical applications. This is why securing the IC fabrication process is so important. Now let's talk about logic locking, which is one of the primary techniques used to secure IC designs. Logic locking works by adding extra logic gates called key gates and key inputs to the circuit during the design phase. The circuit will only function correctly when the correct key is loaded into the on-chip memory. Think of it like a lock and key mechanism, where only the right key will unlock the circuit's full functionality. Uh, there are different types of logic locking techniques depending on type of key gates used. uh, Depending on types of gates used, such as XOR, XNOR, XNOR based, multiplexers based, or lookup table based. These key gates can be inserted using various algorithms like random insertion, fault analysis, or interference analysis. Uh, this is mainly done to increase complexity of the circuit and to make it more secure. Um, However, as we will see, these techniques are not foolproof and can be vulnerable to attacks. Despite its promise, logic locking is not immune to attacks. An attacker with access to netlist extracted through reverse engineering and functional chip can absorb the correct input output behavior. There are two main types of attacks: key search based attacks, and SAT based attacks. Um, SAT based attacks. Instead of blindly guessing keys like key search based attacks, it uses a Boolean satisfiability solver to identify and rule out incorrect keys systematically, uh, and it efficiently eliminates a large number of incorrect key possibilities in each iteration. It requires access to an oracle or a functional chip to obtain correct input output pairs. It works significantly faster than brute force key search, making traditional logic locking schemes vulnerable. uh, Working of SAT attack. The attacker represents the locked circuit as a boolean function cfx comma k, where x is primary inputs and k is secret key bits. Cfx comma k produces the circuit's output for a given x and k. Then the attacker creates two copies of the locked circuit, one with key k1 and another with k2. The goal here is to find an input x that produces different outputs for the different key values. Uh, the SAT solver searches for an input x star such that the two cfx k1 and cfx k2 functions do not equate. The attacker wants to find an input where different keys k1 and k2 produce different outputs. A SAT solver finds an input such uh, finds an input x star uh, x or x star. This means that for at least some possible key values the output is different. uh, then the attacker applies this value to the real unlocked chip. This output y star is this outputs y star, which is the correct key, and their combination should produce correct value of x. Uh, then we eliminate the incorrect keys. During a SAT attack, each cases gives a subset of incorrect values which are eliminated. In each iteration we get few of the incorrect values. This reduces the total number of cases that we need to make. Every such incorrect key is eliminated from further consideration. The distinguishing input pattern x star is found because it caused at least two different outputs from different keys, but many other keys might also produce the wrong output for x star. Any key that does not satisfy cf x star comma k equals to y star, basically the two functions, is wrong and can be discarded. Since multiple incorrect keys will fail this check simultaneously, they all get eliminated at once. Thus each iteration of the attack can eliminate a large number of incorrect keys instead of just one. Let's consider a 4-bit key space, meaning there are 16 keys from 00 to 11111. Initially the attacker does not know what the key is. The first dip x1 x and 1 x1 might eliminate 8 keys in one step. The second dip eliminate 4 more keys. The third dip eliminates 2 more keys. By the fourth dip only one key remains, and that's the correct key. Instead of checking all the 16 keys one by one, the attack solves the problem in only 4 queries. It can also be understood easily by thinking of it as suppose we have multiple choice exam, and there are 16 possible answers. Instead of checking each answer one by one, you ask a smart friend, a sat solver in this case, who gives a single question that is deep. The answer to that question lets you to rule out half the wrong answers at once. After a few smart questions, only the correct answer remains. This is how SAT attack works. It asks the best possible questions, tips that helps to rule out the most incorrect keys in each iteration. Now moving on to SARLock, which stands for SAT Attack Resistant Logic Locking. SARLock is designed to resist SAT attacks by ensuring that each tip eliminates at most one incorrect key. This is significant improvement over traditional logic locking techniques where each tip can eliminate many incorrect keys. In SARLock, the attacker would need an exponential number of dips, specifically 2 to the power of k, where k is the number of key bits to break the locking. For example, if there are 64 key bits, the attacker would need to the power of 64 dips, which is computationally infeasible. This makes the SAT attack infeasible in practice, as the time required increases from minutes to hours or even days. Let's dive deeper into how SARLock works. SARLock uses a comparator to detect incorrect keys. When the key is wrong, it generates a flip signal that modifies the output. The key equations here are flip equals to if the input is equals to key, then it gives us 0, and if it is false, then the output is 1, which means the flip signal is 0. Y lock is equals to Y original XOR operation flip. uh, this mechanism ensures that incorrect keys produce incorrect outputs, making it extremely difficult for the SAT solver to find the correct key. Essentially, SARLock introduces a layer of obfuscation that confuses the SAT solver, forcing it to perform an exhaustive search. Why SAT attack fails on SARLock? The key reason is the exponential increase in the number of dips required. In traditional logic locking, each dip can eliminate multiple incorrect keys, but in SARLock, each dip eliminates only one incorrect key. This means the attacker would need 2 to the power of k dips, where k is the number of key bits. For example, if there are 64 key bits, the attacker would need 2 to the power of 64 dips, which is computationally infeasible. As a result, the SAT attack execution time increases from minutes to hours or even days, effectively rendering the attacks useless. This is significant improvement in security, as it makes the attack impractical for real world scenarios. To further enhance security, SARLock can be combined with strong logic locking. SLL obscure the circuit structure, making it resistant to reverse engineering attacks. While SARLock prevents SAT attacks, together they can form a two-layer defense that secures the chip against both structural and functional attacks. This combination ensures that the chip remains secure even in the face of advanced threats. For example, even if an attacker manages to reverse engineer the circuit, they would still need to break SARLock, which is computationally infeasible. This makes SARLock plus SSL a comprehensive solution for securing ICs. Thank you.
In conclusion, SARLock provides a robust solution to the vulnerabilities of traditional logic locking techniques by ensuring that its state eliminates only one incorrect key. SARLock makes it uh, makes it makes it offers a comprehensive defense against both reverse engineering and SAT attacks. This makes SARLock a promising approach for securing ICs in the globalized fabrication chain. As the demand for secure hardware continues to grow, techniques like SARLock will play a critical role in ensuring the integrity and reliability of electronic systems. Thank you for your attention, and I'm happy to take any questions if you may have.